Okay, so what about this? So, you guys understand what it means to be inscribed in a sphere, right? So the biggest one that'll fit completely inside the sphere, right? Okay, so we've got, what are we trying to minimize or maximize? Volume. So the volume of a cone, there's the volume of cone. Okay, and they drew us a nice picture. So x is the radius of the cone, and y is the height of the cone, right? Okay. Well, it's the whole. That's supposed to be the whole height of the cone. Right? Okay, so there's our primary equation. Obviously, what's the issue with that?
Y is actually y plus 13.
What's that?
Y is actually y plus 13.
Yeah, that's okay.
So we know what x is.
You're right. So the way they've got this drawn, y is the whole thing. So this quantity right here is actually going to be y minus 13. Okay. Okay. So y, and let me change that on here. So y represents, just so we know, y represents that whole distance, right? That's y. Okay, so then we need an equation of constraint, don't we? Right? So what's the equation of constraint going to be? It has to involve, what does it obviously have to involve? 13. Yeah, it has to involve the radius. Without any constraint, the answer is easy. Just make it infinitely big. Make the sphere infinitely big, right? But it's not. It's 13. So then what's the equation we can come up with that's going to relate x and y in 13? Yeah, so we've got this right triangle in here. Whoops. Got this right triangle. And look at the sides of that right triangle. We've got x, 13, and then this side over here is really y minus 13. Right, because if y is the whole distance, okay? So then, by Pythagorean theorem, doesn't that just tell us that x, whoops, out of color, x squared plus the quantity y minus 13 squared equals 13 squared? Okay, so if we were to expand that out, which we probably should do, what's that give us? Y squared minus 26y plus 13 squared equals 13 squared, right? So which variable are we going to solve for here? X squared. Yeah, everybody see that? I've got an x squared there and an x squared there. I don't have a single y, so that's the connection we want to make, right? So we get x squared equals, if I move these terms to the other side, I get that substitution equation. Pause there. Does that all make sense?
Yeah.
Okay, so then if we make our substitution, we now get v as a function of y, because we're going to get rid of the x's, right? So v of y would equal pi thirds times x squared, which is going to be the quantity 26y minus y squared times y. Okay, so we could make that a polynomial. Okay, what do we need? What do we need though with our function? So we're about to just move to calculus mode and make a table. We need a domain, sure. So we're looking at values of y. So what's the smallest that y could reasonably be? There is no restriction mathematically, is there? Right? I mean, it could go, y could become negative, but obviously negative doesn't make sense because y is it's a dimension, right? 0?
13 is
Okay, yeah, right. If we made it 0, that really wouldn't make sense, would it? Think about what that would do. If we made, if the right circular cone is inscribed in the sphere, if y were to go to 0, then the whole cone would sit clear up here. Well, obviously, that's not going to be the greatest volume, is it? Right? We might as well start at when y is halfway down, right? Because if I were to push y up into the northern hemisphere of this sphere, look what would happen. Like if I squeezed it clear up to here, so that were my cone, well, that's going to have the same y value as I would have down there, or the same x value. See what I'm saying? Well, which one's bigger, obviously? The bottom one, right? So for a given x value, you would always take the bigger of the two y values, right? I mean, we wouldn't get the wrong answer if we assumed it was 0, but we're just going to do a lot of extra work for nothing, right? We might as well start y here and then just drag the cone down a little bit to make it taller and skinnier and see how that affects the volume, right? So we're going to go between what two values then? 13 and 13 is a radius, and 26, right? We know somewhere in there's going to have to be a maximum, okay? That make sense? Okay. So it helps to not start at 0. We know we can start at 13. Makes our job a little bit easier. And then, I would say this is a pretty easy one, really, right? This is just a polynomial. Polynomials are the best. They're the easiest ones to work with. Derivatives are simple. What's v prime? Got my pi thirds out front.
52.
Minus,
3 y squared.
okay, good. And so v prime equals 0 when what? When all this stuff equals 0, right? So we could why not multiply by -1 and flip that around, right? So we end up with 3y squared minus 52y equals 0. Just a little easier to think about. So I can factor that. What are my critical numbers then? 0, which is out of my domain, right? And what else? 52 thirds. So there's our one interior critical number, okay? Okay? Second derivative. What's that going to give us?
52 minus 6y.
Okay, and then this would be a pretty simple table. So let's just grab this stuff. Okay, so there's a summary of all the calculus we did. Let's just make our table. So our domain, we said, went from 13 to 26. We had one critical number at 52 thirds. That was a 0 of the first derivative. What's the value of the second derivative there? It's negative. Everybody agree? If I plug it in, okay? So then this is what we thought it would be. It's maximum, isn't it? Right? And the question's asking for what? Volume. Okay, so then what do we do in our table? Really, we just want to know what goes there, right? It's our volume row. So we're just going to plug. We don't have to do, you see, it would be a lot of extra work to figure out what x is and go back to the original equation. We've already gone through the hassle of writing volume as a function of y. So plug in that y value and get a volume and we're done. Okay? Make sense? Okay. So then back to this guy. And this, I want to do this one just because, you know, this is one of those, there's just a handful of problems that, you don't have to do the same one every year, but there's a handful of different kinds of optimization problems that I just want you to see. And this is one of them, where it's a weighted surface area problem. So quick recap. Remember what we were talking about with this one? We had this weird shape where we had a cylinder with hemispherical end caps. The end caps cost twice as much per unit area as the barrel of the cylinder does. If we want to enclose a volume of 4,000 cubic feet, we're trying to find the shape that's going to minimize the total cost, right? And so, what did we say? Well, we know that the cost for the end caps was going to be, if K is the cost per unit area for the tube, right? We don't know what that is, but we'll just call it K. Then we know that the cost for the caps is going to be 2K per unit area, right? Twice as much. And so if we want to come up with our overall cost function, we're just going to multiply the surface area of the two hemispheres, which combine to make a sphere, right, times 2K, plus the lateral area of the cylinder, right, just the tube part, times K. And I think that's just about where we were. Well, so we came up with then, we plugged in the specifics. If the radius is r of both the hemispheres and the cylinder, and the height of the cylinder is h, then 4 pi r squared is the surface area of the sphere. 2 pi rh is the lateral area of the tube. And so we come up with our primary equation. But the problem is we've got r's and h's, right? And so we need a constraint. Well, the constraint is the number. It's the volume, right? So the volume, you guys told me the volume would be the volume of the sphere, you combine both the hemispheres, 4/3 pi r cubed, plus the volume of the cylinder, which is the area of the cap times the height. So you're going to take that area and you're going to carve out space to create volume by moving it up h, right? So pi r squared h equals 4,000. And so we're going to solve for h, because h only shows up once in both equations. So if we just subtracted that term to the other side and divided by pi r squared, first we cleared the fractions, right? I think that's a good idea, because then you don't have to mess around with combining all these fractions, adding and subtracting all these fractions. We multiply both sides through by 3 to clear the fractions. Then we isolate h. Okay? And we make our substitution, and that's where we left off, right? So now we've got cost as a function of radius only. Okay? And what happened here? So when we made our substitution for h, one nice thing happened. We get an r canceling top and bottom. And so our final form of this, let's go to a new page. Okay, so we end up with 8k pi r cubed plus, well, we could just distribute that 2k pi to both terms. So what's that going to give us? Plus 24,000 k pi divided by 3 pi r minus, what do we get here? 8k pi squared. R cubed over 3 pi r. So we can do some cancellation, right? We get one of the r's cancels, one of the pi cancels. Here we get the pi canceling. 24,000 over 3 is 8,000. So we get some good stuff happening. It looks a little better. Okay, so there's cost as a function of radius, right? So we got primary equation in terms of a single variable. What's our domain going to be? Let's go back to this page over here and think about the domain. Okay, h and r are the two variables, right? So we know as r gets big, h gets small, and vice versa. Right, we can see they have an inverse relationship here. So what's the smallest that r could become?
Zero.
I mean, if it became 0, if r became 0, what would that do to the height? It would become infinitely big. So we know that it probably can't actually be 0, but it could approach 0, right? So the bottom end of the domain is the radius has to be greater than 0. What's the biggest it could be? Well, if we turn that relationship around, what if h goes to 0? If h goes to 0, what's the biggest that r could be? Well, r would have to be infinitely big, wouldn't it? Right? Does everybody see that? If we were to split up this common denominator, I'm going to end up with one term that's going to be 12,000 over 3 pi r squared. Everybody see that? In order for that one to go to 0, what's going to happen to r? It's going to have to get infinitely big, isn't it? Right? Does that make sense? Somewhere in there, we're going to get an answer that's going to work. Okay? All right, so okay, doesn't that kind of fit with what we talked about earlier too? You kind of see a pattern here. I don't want to just leave it at that. So if you have a fixed volume, right? Think about what we said some previous examples. Like even if we had a single drop of water, if it's got a fixed volume, if I squish that down, let's say into a cylindrical puddle, right? If I squish it down so the height goes to 0, there's a finite amount of volume there, right? So the radius would have to get infinitely big. Does that make sense? No matter what the shape is, if it's a volume shape, and I'm going to like constrain it so I'm going to squeeze the radius down so the radius becomes infinitely thin, well, if you have a finite volume that you've got to account for, it would have to get infinitely tall, right? We take the cylinder and we squeeze it down. So hang on a second. You know what? That's a little. Okay, actually no. This is what's going on here. If the height goes to 0, what happens to the radius? This one's a little bit. Not that this is that big a deal, honestly. But what happens if the height goes to 0? In this case, what has to happen then to the? If the height goes to 0, how does this shape change?
Becomes a sphere.
Just becomes a sphere, doesn't it? Right? So there actually is gonna be an upper limit to the radius. Honestly, is it gonna have any profound impact on our calculus? No, probably not, because we're gonna end up getting a critical number that's gonna be the same regardless, but you see my point? This is one where, and I think I just kind of glossed through something and made a mistake there, because think about this, I did. If h goes to 0, I've got a fraction. When does the fraction go to 0? No, not,
Pi r.
when, like, if you have a fraction that's equal to x over y, when does the fraction go to 0?
And the top is 0.
When the top is 0, right? So we could go through this and say, whatever's in the top right here, let's just grab that. Does everybody get this? Right? If the radius goes to 0, the height would have to be infinitely high, because the shape would become just like a one-dimensional object. But if the height goes to 0, all that happens is this shape just kind of devolves into a sphere, right?
And the radius would be 21.
Yeah, so if we, oops. So there's the numerator, right? All we have to do is set that equal to 0 and solve for r, right? So we get 4 pi r cubed equals 12,000. What are the math gods doing here? What is that? That's just the volume of a sphere, isn't it? Right? So we're just going to say, essentially all we're doing is we're saying, okay, well, if all the volume goes into the sphere, what would the radius be? So r is just going to equal the cube root of 12,000 over 4 pi. 4 and the 12 would reduce, but we go just get a decimal anyway. What's that give us, roughly?
21.12.
21.12. Well, it's a lot like 2112. It's a number, it's an important number, 2112. If you don't know the significance of that number, you better check it out. It's really important. Okay, so 21.12 is the upper end. 21.12-ish. Okay, somewhere in there we should get a critical number. All right, so calculus time. Is this a good or bad one? I'd say it's not too bad. It's not, the only bad part is we've got this one r on the bottom, but it's not terrible, right? So, okay, so what's the derivative of the first term?
24k pi r squared.
R squared. Okay, here we're going to get
Minus 8,000k.
minus, good,
over r squared.
8,000k over r squared minus
16.
16k.
Okay, I take that back. That's pretty ugly. Okay, so we got to find the zeros of this. So what's our strategy here? What would you do?
Well, k.
No, quitting's not an option. I mean,
Remove a k. Take k
You
out.
could take
we could, yeah, we could divide both sides by k. That's good.
Take an 8k out?
Yeah, we could take an 8k out. Okay, that's going to make that a 3. That's going to make that a 1,000. That's going to make that a 2. That's good. Okay, it's a little better. Now what? It looks pretty ugly when you've got those 3
Now we can
terms.
say by a vowel.
What would you do? Nick, what'd you say?
I asked if we could buy a vowel.
Oh, by a vowel. Oh, I thought you said something else. You know how when you're thinking the right answer, everything sounds like.
Yeah.
So no, by the vowel is probably not our best option.
Could you multiply each side by r squared?
And then
Okay, you could, if you but here's the problem with that. When you start multiplying both sides of an equation by r squared, and you're multiplying by 0, you're potentially, it's okay in this case, you gotta be careful with that. When you multiply or divide both sides by a constant, and you've got it in standard form, you can lose solutions. let's accomplish the same thing, is what you're saying. I've just essentially got three fractions here, right? Do you see any advantage to writing this as one big fraction? Because we're trying to find the zero of the function. Find where the top equals zero would be the critical numbers, and then where the bottom equals zero would be critical numbers where the derivative would be undefined, right? Does that make sense? Okay, so then if we get a common denominator, we're gonna get 3r squared, aren't we? Right, so I could multiply this one by 3r squared over 3r squared. Okay, so times 3r squared. 3r squared, I'm just going to multiply this one times 3 over 3, and I'm going to multiply this one times r squared over r squared. And what do we end up getting if we do all that stuff? So I know I'm going to get on the bottom 3r squared. What do I get here? I'm going to get 3 times 3 is 9 pi r to the fourth. Okay, minus 3,000. Minus 2 pi r cubed. Okay, equals 0. Well, that came out pretty ugly, didn't it? I really thought that was going to be an r to the fourth and an r squared. It just seems like it should be. Okay. So that is going to be pretty hard to solve analytically.
At least we know how to do the problem.
Well, so, but, yeah. But I mean, okay, so we can finish it, but we might just rely on technology. We could do this thing, but it's if we use the rational root theorem, we could find the places where the zeros exist, and then we'd have to go. I mean, this would be a long, arduous problem, right? So what we'll do instead is we'll just say we want to find the zeros of the top of this thing, right? So let's just graph it and find the zeros, okay? So if we want, man, I'm not convinced we didn't make a mistake there, though.
Neither am I.
I'm really not, because it just seems, that doesn't seem quite right to me. It just doesn't seem quite right. We had an R right there, right? So, well, oh, looks good.
R equals 3.27 sounds okay?
Yeah, that seems reasonable. Okay, so I'm just going to put this in Desmos.
We can't know that's the thing. We don't get the fast food understand. Have you seen the 3D animation on the four-dimensional object? It's impossible. Well, it's a representation. It's not accurate. It's a square. Okay. It's a square that has a larger square. It's like the square you don't think about. Okay. Think about a pyramid. Think about a pyramid that slices kind of up. It's a square on top of the and then the biggest one at the bottom gets smaller, goes inside of the small one as it gets bigger and recycles itself.
Oh, cute.
So what do you do?
It's a donut square. No, it's not.
You do donut square.
Oh, there we go. Okay, so this is what we get if we graph that thing. Okay. So I mean, this obviously it's a really tall function. So if you look for, if we zoom out a bunch. Yeah. I want to make this look a little better. So y-axis, let's make it go from,
Negative infinity to positive.
yeah, negative, let's just try like negative 10,000. Well, that looks all right. Up to positive 10,000. Okay, how about if we
You
go
gotta
Getting
keep
better.
going.
100,000?
Keep adding.
What?
Keep adding zeros.
Okay, so this thing is, it looks like it's not gonna turn anymore. So that's really what we want right there, is just that 0, right? So it's about 3.266. Okay.
Isn't that that much?
And what's our upper limit anyway? Wasn't it
21.
21? Well, we can see that there's nothing, I mean, there's nothing between that and 21, right? So in our domain, there's only that 1 0 of the derivative, which is right there. Okay? So 3.266, roughly. All right, so C prime equals 0 at R. Is approximately 3.266. Okay, what about the bottom? Where's the bottom equal to 0? When R is, okay, so the other critical number isn't in our domain, right? The derivative is undefined in a place that's not even in our domain. So we get this one critical number, the second derivative. Now, if we look at the second derivative, do we even want to take it? I'd say we probably do, because we don't want to have to plug stuff into this big ugly function. So this first term, what are we going to get from this first term if we go back to ignore that part? We don't need a common denominator. We're going to get 6 pi r. Everybody agree?
Yes.
I agree.
Second term, we're going to get,
Same. No.
we're going to get
1,000.
plus, right, it's positive, 2,000 r cubed over r cubed. And then the last one, we're going to get just a constant, right? We're just going to get minus 2 pi, 2/3 pi.
Yep.
Okay, well, if we plug in a number like 3 point something, would you agree we're going to get a positive result,
Sure.
right? This one's going to be like 3 point something. That's going to be a pretty big number. That's going to be a reasonably big number. That's not a very big number, right? That's less than 3. So it's going to be C double prime of 3.266 is definitely positive. We don't care what the value is. We just know it's positive. Okay, so what's this tell us with our table then?
It's a minimum.
So we went from 0 up to,
21.
oh, that's right, I forget that. And 3.266. And that was a 0 of the first derivative, positive second derivative. So what is that? Minimum, which is what we wanted. And so that's going to be the radius that minimizes the cost of this shape. Okay?
What was the C again?
Cost.
Oh.
Remember what we were trying to do way back when was minimize the cost of this weird looking tank. Right? And so the math gods answered. We want to know
But it says find dimensions.
dimensions.
H2.
Okay, so how would we find H?
Put R into that.
Plug that R back into there, right? So what does that give us real quick? If we just plug in 3.266. Two, three, something like that, probably.
I don't think this is right. It's gonna get big
I don't think it should be that big.
About 114.
Really?
Yeah, I got 115.
Man, that seems weird. Oops. So 3.266 store is X, and then let's do this. So quantity 12,000 minus 4 times wow. Is that right? That can't be right. We had to screw something up on that. There's no way that's right. No way. So the moral of the lesson today, I guess, is that sometimes you make mistakes. Oh yeah, something's wrong. Should have been 1.42, should have been the radius. So what the heck did we do wrong?
We forgot to divide by 2. I recognize that, I just didn't want to tell you.
Oh, okay.
Oh, wait. Oh, no, they're not.
I don't know. Man, that's really gonna bug me now.
I mean, I already, there's like a claim that's $60 that I can get 12 grand, so.
Okay, let's see if we get the same.
Anyone want some stuff? There's 60, there's 62%. They're loose.
Oh, I was looking at the wrong one.
So maybe we were right?
No, we weren't. The radius should have been 5.636, and the height should have been 22.545. But I still am not seeing what we did wrong. So 8K pi r. Oh. Oh, how did we get a cube there? It should have been a square.
I had squared and then I saw it.
Very sorry you're not.
So I erased it.
So, oh, it is squared. Yeah.
Were you actually right?
The difference was 16.
H. Yeah, that should have been squared. Okay, that would have made this whole problem a lot easier if that were squared. Yeah. Okay, everybody see what we did? What I did?
No.
You guys didn't catch me though, so you're responsible. So that first term, when we substitute for H, there was no reason why. Where did that squared somehow become cubed down there?
Probably the height.
Yeah, it shouldn't have, right? That should have been a squared right there. If that were a square, just think how much easier that would have made things. Then we would have ended up with two r squared terms on the top that would have been like terms, and then just a constant. So we could have isolated when we set the top equal to 0, gotten r squared by itself and square rooted both sides. Would have been a lot easier.
Did they call it?
Something didn't seem right with that when we were going through it.
I don't know how you can tell that it's straight. Like,
I think we use it pretty
tell that part of
I don't know. I think we were foiled by the priests of the temples of Syrinx. If that doesn't make sense, you better do a little
All
research.
the questions
Oh,
are
yeah, it was just like,
Really?
There's one like
not very much awesome.
that exact. I'm pretty sure that exact